Hi, everyone. My name's Lingni. I'm a research scientist from the Surreal team. So today, I'd like to talk to you about Nymeria++. This is an upgrade to the previous released Nymeria dataset. And we want to upgrade the dataset to empower human motion understanding research in an even better way. So for people who are not familiar with what Nymeria dataset is, this is basically a massive collection of human motion in the wild. The team released the dataset last year at ECCV 2024. So the dataset was recorded with multiple Project Aria Gen 1 device and Gen 1 alike wristband and motion capture suit. All of them are time-aligned and spatially localized in one metric 3D world. And the dataset is annotated with the ground truth, body motion, the human written narrations. As of today, the dataset is still the world's largest human motion in the wild and the largest collection of human motion with natural descriptions. So to help you visualize the quality and diversity, this video actually shows you random sampled 100 snippets from the Nymeria dataset. All right. And on this slide, I briefly summarize the key statistics about the dataset. As I mentioned, the dataset is actually fully released last year. So with the QR code, it will bring you to our website where you can already download the data, the code, the paper, or just simply visualize the data online and filter the sequences and modalities as needed by your research. Before diving into the details of how we upgrade Nymeria dataset, let me first briefly mention a few research study cases that are uniquely empowered by the dataset. So the first one is the algorithm that we developed to track egocentric full body motion from a single pair of smart glasses such as Aria Gen 1. So this is a very challenging problem because with the form factor of the smart glasses, even with multiple cameras, they hardly observe or provide any self-observations. And traditionally, in order to solve this problem, people typically need to wear multiple motion sensors in order to estimate their own body motion. Now, this was changed when we start to use Nymeria, where we show that given a large quantity of training data, we can actually learn a machine learning algorithms to infer the egocentric body motion. We named this algorithm HMD2. So at its core, this is a diffusion algorithm that generates the full body motion conditioned on the headset trajectories, the hand tracking, image embeddings, as well as the surrounding point cloud. Now, in this video, we show the result of HMD2 in tracking the full body motion from a single pair of Aria device. Again, I want to remind you how little information the egocentric videos actually captures the self-body motion, yet trained with a large quantity of data and leverage the environment context. The network is actually able to make very reasonable predictions. So the nice thing about the algorithm is that it actually explains the ambiguous motion state by a probability distribution, since we use diffusion to frame the problem. And to visualize this distribution, we actually sample the model 10 times and overlay the output. So if you focus on the hand, you will notice that whenever the hand appear in the view, the distribution is actually collapsed to a very tight distribution. However, when the hand move outside the field of view and hand tracking become unavailable, the model is also able to give you very diverse and equally plausible poses. Now, the second case I want to share is another powerful modeling technique that we'll also explore to build generic foundations for egocentric motion understanding. The algorithm is what we call EGLOM. So this is an algorithm designed around 3 principles. First, we want to model the human motion as language in order to harvest the power of large language models. So this is logical because both language and human motions are sequential data with very strong continuities, where transformer and next token autoregressive prediction is very suited to model the transitional probability, the short-term and long-term context dependencies. So we want to use, the second one is we want to use a generative modeling technique. So we can sample the distribution to still represent that ambiguous motion state. The third principle is we want to model actually the joint distribution of all the modalities together. For example, the body motion, the language descriptions, as well as the multimodal sensor measurement. By doing this, we open the door to unify the framework to achieve multiple motion tasks by later marginalize the joint distribution. For example, we can now condition motion from video or text or vice versa. So this basically brings EagleOM into a very similar training paradigm as large language models, which means we will tokenize the human motion with VQVAEs, and then we expand the vocabulary of large language models by pre-training, and the last we fine-tune the model to achieve multiple tasks. Now, I actually want to show you some interesting tasks that EagleOM is able to perform, starting from a relatively simple one, where we use the headset and erase the 6-DOF trajectories to predict the full body motion. So this is typically known as the 3-point body tracking problems in graphics. We compare our solution with 2 state-of-the-art solutions as Avatar Poser and Body Fusion. So earlier I said this problem is actually relatively easy because if you know the 3-point trajectories from your head and hands, your body motion, especially the upper body motion, is pretty well constrained. However, as shown in this video, EagleOM often gives much more stable and accurate predictions of the lower body, while the other baselines from time to time struggles. This is also observed in the second examples, where our algorithm predicts more plausible solutions with respect to the environment, whereas the baseline algorithms often penetrate and produce implausible motion. And let's remember that this is a very challenging cases where the lower body is actually not observed by the input. Next, I want to show you a bit more challenging cases where we remove the raised conditions and only use a single point to infer the full body motion. And we compare this our algorithm with Eagle, which is a diffusion-based solution. Now, what we observe here is EagleOM is able to give much more accurate poses in general. And in this example, we also observe that often EagleOM is able to give more accurate and more energetic hand motions. Last, I want to show the most challenging task that EagleOM is able to perform, which is to jointly predicting the parametric body motion as well as the language description. So for this task, we actually didn't find any existing solutions. So we shown the output of our models and compare the ground truth motion to our predictions. So in this demo, what you see here is the description on the right is often very detailed with in-context informations. For example, it is not just describing how the person is moving the body, but often describing the environment where the person is looking at and how the hand is interacting with the environment as well as where the person is. Now, this is just another example to show you a diverse scenarios of what EagleOM is able to handle. Okay, moving on with the third study case, which is for the axial body tracking. You might think people have been studying this problem for decades and it must be a solved case. But actually, if you take a closer look at existing solutions, you will notice that most of the algorithm largely focused on single view videos, which leads to the scale ambiguities. Furthermore, cameras are often static or only move slightly or slowly. This is actually not the case when you wear smart glasses on your head. In this setting, we emphasize that any solutions to estimate the axial body motion should be spatially aligned with the same metric 3D world with the rest of the spatial context output. So in order to address these challenges, again, we train an algorithm based on the Nymeria dataset. And here I want to show you the exciting early results that we already achieved in our early experiment. So actually what we're showing you here is the algorithm trained on Nymeria dataset but inferred on ARIA Gen 2 device. So what it's showing here is our colleague Nan grabbing lunch with his friends at the cafeterias. As he moves around, we track almost every single person observed in the egocentric cameras. Note that how many people are populated in the same metric space and are all spatially aligned with the world coordinates. And I also want to point it out that thanks to the collectively 270-degree field of view of ARIA Gen 2 device, people behind the egocentric wearers is also well tracked. It's almost like you have invisible eyes. Now, the detail of this work will come out soon, so stay tuned. Now, in addition to the work that is mostly developed by our team, we also noticed that the dataset has been gaining attention in academia research. Listed here just a few recent publications where we see research projects uniquely enabled by our dataset. For example, people are using the IMUs to infer the body motion as well as to output the text descriptions. They also are using the body motions to condition video generation models or even jointly predicting both egocentric motions as well as the videos. All right. So let me switch gear and start talk about how we actually make the dataset even better into Nymeria++. So this brings me to this teaser video that gives you a glimpse of what Nymeria++ actually is. So I'll just let the video play for a moment. Obviously, there is a lot of things going on. There's body motions, and there's something like bounding boxes. So let me actually break down Nymeria++ into 3 major axes that describes the upgrade. The very first upgrade is actually along optimizing the body motion as well as the body shape. So in the previous Nymeria dataset release, we actually mostly solely relied on the Axon's motion capture suite to give us the ground truth motion. The only modification we did is to align the body motion into the metric 3D world as the rest of the ARIA device. The motion artifacts, however, are often not addressed, such as there's foot sliding and inaccurate end effector motions, especially observed with the hand. And in the previous release, we also use a relatively simple algorithm to retarget the Axon's motion into a Meta's human model without much care. This is mostly for visualization purposes, and this also leads to some non-ideal shapes. Let's see if I can play this video. It's really hard. Okay, it doesn't seem to like to play. Anyways, okay. Anyways, if the video doesn't play, but with the view, you can already start to notice on the left, you see the original vision, the original body retargeted into the human model. On the right, you see the latest result from Nymeria++. So in order to get these results, we actually improved the upper body motion using the wristband tracking, which is way more accurate than IMU-based tracking from the motion capture suite. We also reduced the foot sliding using the velocity of the feet as well as the foot contact with the floor. The third thing is we also retarget the Axon's kinematic motion into Meta's latest and greatest human motion model, which will be released by the end of this month. And the last thing is we paid particular attention to how we retarget and optimize these shapes and motions, and particularly also retarget them into the simple format, where we heard a lot of feedbacks of how people would like to use these different human models in their research that can potentially unify Nymeria with the other motion dataset out there in the wild. All right. In addition to motion, the second axis we upgrade is actually to enrich the dataset with dense 3D bounding boxes annotations for almost all 900 indoor collections. The reason to add this annotation is motivated by the principle that the human motion is actually a function of the environment, so the environment should be a very useful context to infer body motion and understanding body motion. And with these annotations that we did, we're not only including most common objects categories, such as the chairs, tables, plants, storage, cabinet. We also include structures of the space, such as the walls, floors, windows, etc. So in this video, we actually shows the fly-through of 47 unique Airbnb locations, which are all densely populated with these bounding boxes and structures. And to help you further visualize the quality, we projected these 3D bounding boxes into the ARIA and RGB view to show you how accurate and dense annotation is. I also want to briefly mention some of the statistics of these bounding box annotations. So they are mostly derived from 47 base map annotations, where we have all the recordings spatially localized into the same coordinates. However, we do not do a simple transfer of these base map annotations into individual recordings. We also fine touch on each individual recordings to remove objects that has been moved and refine the annotations. So this brings us to 19 predefined object classes, where we have a little bit close to 12,000 semantic unique objects. We also add a free-form categories that can describe anything that you can observe at the home. So this brings us to another close to 10,000 unique instances of objects that you can observe at your home. Now, the third upgrade we did is actually focus on extra data and modalities that are previously excluded from the release due to various reasons. And these additional modalities include additional hours of data, new base maps recordings that we use to annotate all the 3D bounding boxes. We also are including 600 hours of wristband videos, where they can be particularly interesting for robotic learning because they provide video perspectives coming from your wrist, coming from your hand. The fourth thing is we're also including 600 hours of audio data recorded also with the ARIA device, particularly useful between the participants and the moderators. There has been a lot of interesting conversations going on. Last, we're also considering adding object dense reconstructions using the ShapeR algorithms you just heard from my colleague Yawor. Okay, to conclude my talk, I'd like to show you this video. This is actually not a Nymeria dataset, but it's an algorithm that's a lot of algorithms that is built on top of Nymeria dataset, and this is inferred on the ARIA Gen 2 device. It actually shows you a very good concept of what we want to build and achieve with the Nymeria dataset. And with that, I hope this can inspire people to better use, make better use of our data. So Nymeria dataset will be released by the end of this year. Please stay tuned, and you can get the update from our projectaria.com. With that, I'd like to thank all the amazing people behind this work. Thank you.